All right, so we continue our workshop here. It's an immense pleasure to introduce Professor Lino Grama from UNICAMP, who is going to tell us about recent developments on generalized manifolds.
Okay, thank you. And the title of the talk is Spherical T-duality and generalized log. These are just a report of the work in progress. With Ludwig and Leonardo Cavenaghi, also here. Okay, and then the plan will be the first. We just a quick review of T-duality in the sense of the Bognet Hamilton and and the second, we explore spherical T-duality and show some applications of this concept in our working progress. And the third part, we have tried the proposal on the definition of the generalized log transform. And investigate how to this two and three are related. And okay, let's just to recall. Bognet Hamilton MRI. Mostly 2004. There is a proposal approach. I don't know. Okay. This guy is a physicist, and there is a lot of theoretical physics behind this motivation, etc. But there's a proposal here is a duality for principal torque bundle. With H flux. This is for us is a closest to zero. Okay. And the intuitive idea is exchange charge is a curvature too far with the H flux. Will be the charge too far. This interchange between T-duality manifolds. Okay. And then the definition. We say T, W and J are T-dual in that sense. If we have this the follow diagram, we have the T, H the product bundle over the same base. We have the correspondence space here. Here. This is a fiber product. And omega and we say these two pairs, two pairs are T-dual if the and we change T-dual if this form is the F for some F in the H2 to N. This is called a correspondence space, and we are called this pair are T-dual if this three form here are exact, but not for every F. Just need to consider F invariant on the fibers. And okay, and in a sequence of papers, the
Where's the question? So this E and E check are usual SYZ T-dual.
oh, this is a not. I understand your question. You are asking if this if this dual coincides with the XYZ.
What the relation?
Yeah. I know this relation for elliptic curves and for K3. Okay, in general, I don't know. Okay. But for the elliptic case, yes. And then for the K3, as Todos bundle, due to elliptic federation is also, but in general. Okay. And then a sequence of papers. This guy proved that a lot of implication. If the pair are T-dual, you have a lot of consequence in topology in the KT, etc. And it's worth to mention here. We have some results of Cavalcanti and Boccelli. That is compatibility of generalized complex structure and T-duality. In the sense, we have some, if you consider the double, the T star T, and we put this H to be the Savela class of the Partouche de Courant bracket here, and the same here. And if the pair are T-dual, we have this isomorphism of this Courant algebra. And we can transpose the sections, compose it with snap. And in that sense, that one generalized structure here corresponded to another generalized structure here. And in some cases, we can produce like mirror symmetry in this context, maybe. That's a lot of examples, like in the curve in the K2. If you start with some symplectic structure here, put this in the language of complex structure, apply to this machinery, and then we arrive here will be some complex structure. And then we have this compatibility for this T-duality. And in the sense that this means we have isomorphism of Courant algebraic related to the pair. I just simplification, but this is the whole story here. And in some cases, we can interchange this symplectic and complex structure. Okay, now we move to another kind of duality, also introduced by this guy, a little bit more recent. This is called spherical T-duality. This is openet, everything, and not type. Now we are going to produce some duality, but not for the torus bundle, but for the SU2 bundle, spherical bundle, S3 bundle. And we start with P and on S3 bundle. And now our flux lives in H7 of P, and then we consider a pair bundle, comma H. And the T-dual, or spherical T-dual, will be P hat name, comma hat, where P hat and is S3 bundle with C2 check is by step over H. Here we are considering this talk for the simplicity any to be four-dimensional. In most cases, we consider n to be S4. Facilitation is relation with equal in the correspondence space. Okay. And then we have some diagrams like this. We have E, we have 1, 2, D, And in this talk, we consider M to be S4. And we have this correspondence. In this situation, we have the correspondence S3 bundles. Pi with H4 and Z, and given by its correspondence here is given by the second Char class. And in this particular case, we have H4 of S4 Z is equal to Z, and the correspondence is given by the second Char class of this associated bundle P SU2 H. And the theorem, the first theorem of this three movement headed with Mackay, and in this situation, there is a guaranteed existence of the spherical T-duality. There is a theorem movement headed with Mackay. That is if P be a S3 bundle, with the second Char class M, and I consider H with the H4 of P, and suppose there exists a S3 bundle P hat such that the second Char class of P hat is equal to push by form. Then one then exists H hat H7 such that this H is a C2P, and the second H is unique. Okay, up to some cup with this. Okay, this is the structure theorem we are using, and now we are deduce how to use this in our situation. Okay, because now we are going to investigate this. This is the first step of our history. Because we are going to explore a family of the S3 bundles of the S4. These are called Müller bundles. Okay. And then now we apply this theory to a specific case of Müller bundles. Okay. And now there's a family of examples. We are working on the original. These are the called Müller manifolds. Okay. And then we are considered as one and B This is a spherical bundle. This is a linear. If the structure group is okay. This is a okay acting in the sphere in the usual way. And we have the set of Sk-1 bundles over SCL. This is in correspondence with pi L of SCL. So if you fix K is equal to L is equal to N is equal to 4, we have the S3 bundles over S4 will be parameterized by P3 SO4, and then this is P3 of S3 plus S3, and then this is Z plus Z. And that is for the each pair of integers we can produce in a S3 bundle over S4. And then these numbers will keep with us for all this construction. Okay? Actually, are just maybe provide a lot of interpretation for different these two numbers, the combinatorial numbers. Sure. Okay. And then now just this appears like a Miller bundle. And then the Miller construction, just to recall very quickly. The Miller construction, we pick two numbers, M n, in Z plus Z. This is the pi 3 of SO4. And we consider this Tmn a map for S3 to SO4, and we pick X and associate to map Tmn X. This will be just from H to H, given by V, and associate to Xn, V, Xn. This is a that will be a representative of this. And
so is it easy to say how it generalizes to arbitrary K and L?
Okay, you mean for the building, because we are going to build in exotic manifolds, right?
In general, this Miller construction, so does it is there an easy way to write down this
this map here, the representative here. I guess for the constructing another sphere in high dimension is a different way.
No, yeah, it's different. Yeah. It is parameterized by this PL minus 1 of CO.
Yeah.
So
I have no control.
yeah, no, not at all. Yeah.
Sure.
Yeah, this is very particular for the 7-dimensional case.
You can produce it 8-dimensional, 10-dimensional, 11-dimensional, but it's from the different way.
Yes. Another one classical example would be like S15, that are the Shimada spheres, and these are completely different. There's no way of.
Or even the S8 is quite different.
Yes, indeed, S8 it must be way different because you only have two smooth structures on the 8-dimensional sphere.
Yeah. This is already 7-dimensional case.
Yeah.
These will appear because actually these two guys, more due. For instance, it's not because in the G Cavalcanti, because in the duality you can generalize complex structure to put it one way to the other, but it's not clear which kind of structure we can transpose in this spherical one. It's not clear until now. We have some guess, but maybe in the next conference. But because the generalized complex structure doesn't work here, because it's ordinary. But this is a question, actually. And our contributor knows a lot of things.
But there is an infinitesimal version of it, which is what they do in the sense of the Lie algebra on the fibers and the functions on the bottom.
This is a very good question. For this original duality, for the order duality, that is a infinitesimal version. We did this with Juliana,
But in this case,
and not investigate. Probably.
probably, yeah, because of
Probably
the specific
yes.
map.
Yes, probably yes. Needed to write. Yeah, probably yes. Okay. And we can introduce this. This is a completely very beautiful, very classic. G, we are picking X, G, G, X. This is this pair belongs to S3 plus S3 or X. G belong to X. We are going to do is we consider the T4 times S3, and the boundary of this is a S3 cos S3, and we are gluing in another copy of the S3 cos T4. We are gluing by this map. F, T, N, A. Okay, and then we are arriving on this space. M, N. Okay. And this is called Mueller bundle. Okay, and this is a theorem, very famous theorem of Mueller, and that is Mn. The manifold is homeomorph to S7 if and only n plus n is equal to 1, but not diffeomorph. If n is equal to 2. In particular, this this m to minus 1 is a very famous. It's called Grama. This is a building by the app. It's a very beautiful. We call this sigma 7 Grama. But you have some work of Eus Kuiper. They classify all the possibilities. Okay, and now our first remark is this kind of bundles, in some sense, are preserved by spherical T-duality. In some sense, we can reduce one to another by duality. Each water are duality one of another. Let's put some precise way. We can this family are disclosed under the spherical duality. This is a proposition. Cavenaghi, so it's we start with this n and n, or let's put it in a more simplified way. N, okay, means n. With now 7 4 H. Just consider the class J. I explained because remark here. 87 of this and then the constituent integers. This is isomorphic to H4 of S4 Z. This is Z. Just to put the clarity here. Here it is a hypothesis to put this S4 to simplify this. This argument. And in this case, this pair here is spherical T-dual to N J minus J N. We have some symmetry here. Okay. In particular, we can produce one usual sphere. We can produce two. We can produce weird duality or not exotic sphere. Okay. If k is equal to 1, we have n k 0. It's all these are homeomorphic to S7, but not different form plus 2n squared plus equal to 1 more 7. This is a lambda duality. And the same here for v1 plus 2 j squared not 1 more 7. And the first remark is we can some sense jump from the one exotic sphere to another via T-duality. And now I'm going to start to just generalize the block transform. But before, just to remark this kind of construction here is one of the most important in duality, because we are going to understand that this log. First, the log review, just put a quick review of log transform, but more in the sense of differential, in the sense of the decompose of disks. The log transform in the sense of decompose of disks, analyze how to glue this, how to cut the fiber and then glue the another piece. Okay.
Lino, I just have a question. In the definition of the spherical duality, what type of information is there in the middle term?
In the correspondence space.
Yeah, you have the explicit automorphism at the level of homotopy
But
type.
you are asking this example or in general?
In your definition, it's just I don't recall.
Yeah, like the fiber space.
You just get the differential form.
Yes.
No.
Yes, in general, it is the upstairs, right? What integrates is the shared Simons form.
The thing is, I just wonder because there is some specific automorphisms that one is using, and the differential form is just the rational homotopy type of the map.
Okay.
But not the map itself. The map is mapping the mapping.
Yeah,
clutching,
just geometric.
the
Yeah.
clutching function.
Exactly. Yeah.
And so the question is, what is that is kept in the definition? The clutching function or the differential form associated to the clutching function?
I guess is that they're related.
Yeah, but I don't recall if there are no torsion. Well, it seems there are no torsion classes. But so I suppose because it's C or Z, then you can just recall the generating function, like homology class, and you can construct that.
Exactly. This is the generic.
Okay, so I see that.
Okay.
Yeah.
But Yeah, but in this situation, you are put a lot of more. The hypothesis like the basis.
Yeah,
this is a direct thing.
No, of course, it's using S4. And then another question, just I don't know, but do we know the homotopy type of the diffeomorphism group of this S3, diff S3? Because SO4 maps to diff S3. Is this the same homotopy type of the two? So the question is, any spherical bundle arises as SO4, as a map to SO4?
Precisely, over S4, yes.
Yeah, because
So that means they have the same homotopy
diff
type.
S3 is SO4.
That's what my question. Diff S3
No, yeah.
is
Yes,
This
is true.
the same.
Yeah. But this is actually related to the upper dimension.
Yeah,
No, dimension more.
every S3 bundle that's associated to SO4 bundle, like with structure group as SO4.
Principal or not?
Yeah.
We are not.
No, that's why I'm talking about
Yes, bundle.
spherical bundle.
Bundle.
Mhm.
Bundle.
We
Bundle.
need diff S3.
Exactly.
Some of them are principal or not. Okay. But you can choose this situation more very precise.
You can analyze them inside the SO4 preserved orientation. This is true.
Okay.
Yeah, but I think something worth to mention is that on the correspondence space difference, that's something that may appear elsewhere later, is that the difference, because you have zero in homology upstairs, and the form that you realize this is the Sherman-Simons form. Yeah, upstairs on the correspondence space.
I'm not put a lot to how this here, but the afternoon, Leo will be working out probably very deep in this direction, okay? Just to mention, because this is our second example, okay, yesterday appeared in the NS call. This manifold, this is the Hopf manifold, or high dimension Hopf. People call generalized Hopf, but this maybe can produce some confusion. We are fixed, and this law of one, and we consider this manifold n one. Then this is homeomorphic to S7. Okay. This is a n10. And we have the homotopy Hopf. Homotopy Hopf. I don't know if it is good name or not, but what the homotopy Hopf is just homotopy sphere times S1. Will be n n1 yes, n times S1. This is the homotopy Hopf. And then we can apply this duality, this theorem holds here. We can adapt this action with the fibers here, fiber bundle here. And we can produce another theorem. We can determine when complex structures on exotic Hopf are non-equivalent. For the equivalent, we need to work out a little bit more. But in the non-equivalent in the exotic disease space, we can detect this. And this is done by analyze the hot diamonds. Behavior under T-duality. This is a like the first manifestation of kind of cover some kind of mirroring because you can symmetries in the hot diamond between the spherical dual manifolds. And this is and in particular this gives answer for the basic or Van der Ven question about this how to behave this complex structure on this space. But you can just for negative, right? Detective no equivalent. But for the equivalent, we are working. Just need to work a little bit more. Okay, and then now the just pass to the another part of the talk is the part of the log transform. And I can tell the end of the history. We are going to propose general log transform in high dimension. In this specific case, we are going to show that
What was this last sentence in parentheses? The last sentence.
analyze the hot diamond behavior of the hot diamond under the T-duality.
Under the door.
This is the and we are going to propose an high version of the log transform. The proposal, but in this situation we will show that the equivalent or version or the proposal of the high dimension log transform into T-duality, spherical T-duality, and then we need to talk to Ernesto to compatibilize all this new version, but stop in the second part. No, this is the third part. That should be called four-dimensional log transform. Okay, and we start X with a four dimension, and we consider the phi X over sigma elliptic fibration. And we consider the fiber is a tall, and on a regular fiber, F. Okay, let me put in the different way. We say the X prime is obtained from X by a log transform if on a regular fiber, if it cuts a tubular neighborhood mu F of F and glue T2 minus G2 via oriented reverse. Diffuse phi times S1 in the boundary of this tubular neighborhood. Okay. And the multiplicity of this log transform is the absolute degree of this map. We have the multiplicity of the log transform is the degree of boundary of me and composed with phi X times S1. And in some case, okay, we can show this the neighbor, the boundary of this neighbor is also T2 as times this one. This is T3, and one relevant part here is understanding the diffuse of T3 for T3. And okay. Let's put this in the more precise. For instance, just remark. We can consider this S3 cross S1 plus 2. This is the Hopf. This is the Hopf surface. And here we consider the Hopf map in the first factor. In the first factor here, we consider the Hopf map, and the coordinate here is a torus, is the elliptic fibration. And in this, with this in mind, now log transform will be x1 times d2 going S1 times S1 times D2 under some diffuse psi, and psi is from the T3 to T3. And x prime will be S1 D2 going along another diffuse S1 times S1 times D2 for some diffuse. This psi is a diffuse. In this, for this usual S3 cross S1, you can put this explicitly. So T3, repeat 2, the psi, and go to psi. And if you move from this diffuse to another, you can, doing this, you can proceed in a log transform. This procedure in the differential topology is very, very understood. And for instance, in K3 surface, you can produce exotic K3 surface. But for Hopf, you cannot produce now. These are very recent, not so old results. 10 years ago.
2008.
And for this log transform cannot produce exotic Hopf in the 4 dimension. Okay. But in the high dimension, you can do the 7 dimension. We are going to show that you can produce exotic Hopf done by this version of the generalized log transform, and we just adapted this definition. We just consider a fibration, a bundle, and they cut along some fiber doing another piece. But okay, this is a little bit late. But now we are going to start to collecting this analogy, and this fits very well. This is why Mel will show me in the afternoon, for instance, the concept of nuclei for this the log transform. You can recover, and you can recover a lot of algebraic groups that Ludwig will explain, and the analogy will fit very well. Okay, just to finish. This is a taxation of this just 5 minutes. Definition. We consider N, L, homotopic sphere, 7 dimensions. homotopy sphere. And then consider S3. S4. Here it is the structure group is S4, SO4. And with this bundle, we will induce another bundle, L, S4, L, times S1. These are P, 1, these are pi, these are pi, P1. This is just projecting the first. No. This is impossible. This is a projection the first coordinate. This is a producer compose. This is a bundle. This is the Hopf homotopy Hopf. And we call M prime is obtained by log transform. Log transform on fiber F, on the fiber F. If we proceed in the same, okay, cut a table, a tubular neighborhood of this fiber and glue it G4 times S3 times S1. Okay, and it's worth to mention here that is this fiber here is a Hopf, 4-dimensional Hopf. Okay, this is another elliptic bundle with cut tones. Here we are cutting Hopf circles, cutting and then gluing for some different reversing the orientation. Okay, and
you're cutting on the base on a contractible,
yeah,
or you're cutting on a 3 sphere or
in the base. I mean, no, for the on the regular fiber.
I use choose a point.
Yeah. Okay. Because this is a bundle, so it is also simple. We are working on singularities also, but our first remark here. Oh, actually, your this to finish to make sure our scaling. And let S7 plus S1. This is the H-dimensional Hopf. Okay. Then this sigma 7 Groma-Meyer. This is a sphere of Groma-Meyer. This is actually a sphere of Groma-Meyer. Can be obtained from S7 by log transform in this procedure. Okay, but this is better, even better. This is the not just actually this is a corollary. The real theorem is here. If you have T-dual pairs, and one then within a class J, and J. we know that the dual pair have this presentation. Okay? Then Nj1 J can be obtained by a log transform from the fibration S3 plus S1 and then times S1 S4. Okay, this is the, in some sense, okay, in this very precise sense, this T-dual in the generalized log transform are, for this family are the same. Okay. And then the sketch of the proof, if you analyze very carefully the definition of these T-dual pairs, the map to glue this guy encoded in this diagram. You can do this very precisely. Okay. This, when you put along the Hopf surface here, all the information to glue these two pieces are encoded in the T-dual. And in this sense, the both concepts are equivalent. Okay. And this is the open to us a lot of possibilities to investigate new families and analogies, and we are okay. This is an ongoing. We are developing this, but okay. I guess it's and then afternoon, Leonardo will continue to discuss this. Thank you.